Okay, so for the transport protocol, we have covered UDP and TCP, and we know that UDP did very little. It just provide port multiplexing and also a simple checksum for the error control. But if there's an error, then it does not try to recover the error. Just drop the frame, just drop the segment, and it does nothing else. So UDP is very primitive, and it's good for, and it's connectionless, so it's good for some application that does not require reliability or not requiring flow control. Okay. And we have seen TCP, which is quite complicated because it tries to be reliable. So it has many mechanisms built in with acknowledgement, with the sequence number, and with the window retransmission, sequence number, acknowledgement, and retransmission mechanism. And in order to prevent congestion and resolve congestion, it has exercised window-based flow control and congestion control. And we have seen that. And the window size could grow or shrink depending on the condition at the receiver and also at the network. So we have seen the TCP and UDP behavior, and we have seen the socket interface, how they are implemented in the kernel to support the application, to support the upper layer application to use a UDP socket and TCP socket. And we have seen that we provide additional socket interfaces other than TCP socket and UDP socket that allow applications, especially application programmers, to access the lower layer, meaning by passing the TCP and UDP or by passing the IP layer to gain the access to the link interface, link layer. Okay, but there's one thing missing that we need to cover here is if you are real-time application, then you need to consider whether you want to use TCP or UDP. But if you are real-time application, you will find that UDP is too primitive, where you would need additional support from UDP. On the other hand, you will feel that TCP is overkill, and some of the features in UDP is not desired in the real-time application. We have mentioned that some real-time application, especially the hard real-time, we have differentiated the term hard real-time and soft real-time, where voice over IP, IP telephony is the hard real-time application, and voice over IP and teleconferencing are hard real-time applications, while voice, audio or video streaming are soft real-time applications. For those hard real-time applications, they would not need the transport layer to do retransmission. They don't like that. The retransmission are kind of redundant, We don't need retransmission because the retransmission will be too late for the hard real-time applications. In the meantime, we have mentioned that for not just hard real-time, but also for sub-real-time applications, you can't do much flow control on the traffic sources. The traffic rate really depends on the codec. If the codec decides to pump 256 kb per second, then you couldn't flow control this flow to say 128 kb per second. If it pump out this amount of traffic, 256 k, and you flow control to 128 k, then that means there'll be 50% loss. 50% of the stream will be lost, and then the quality will become bad. So for real-time application, either sub-real-time or hard real-time, the network shouldn't do much flow control on them. The rate really should depend on the codec. So on the other hand, you should expect the codec to adjust the rate when the network suffers congestion. The network shouldn't do flow control too much on them by trying to reduce their rate to a half. No, you don't want to do that. Okay, the codec should be adaptive and adjust to the network condition. So that's the reason why flow control or congestion control exercise by TCP is not good for real-time applications. So we have seen that TCP is not good for real-time, and UDP is not enough. And we need to find out what additional support the real-time application need. So we have raised 3 issues. The first issue is about multi-homing and multi-streaming, where you would have a session, a real-time session, traffic session, constructed from through multiple interfaces. It's possible that you would have multiple connections constitute a session. For example, you would a video program on IPTV would have one video stream and probably 2 audio stream because it's stereo, so you might have 2 audio stream, and then 1 text stream. So you would have at least 4 streams constitute a video session, and they might be from going through from different network interfaces and from different sources. So you would have the problem of multi-homing and multi-streaming, and you need to differentiate. You need to differentiate these streams. So you need the ID. You will see that we would have this stream ID added in the protocol header in RTP. So you need to identify the stream. The second issue is about the rate, the flow control and congestion control, especially flow control. We have mentioned the AIMD additive increase and multiplicative decrease in TCP The AIMD stands for additive increase, multiplicative decrease. It's not in TCP. It's not suitable for streaming. As we have mentioned, that the rate really should depends on the codec. Okay. However, there's some argument saying if the internet now still have TCP dominate the traffic. The traffic is still dominated by TCP, not by UDP. That's because right now the majority, I think P2P traffic account for 70% of the internet traffic, P2P. Okay, and P2P, we have mentioned that P2P use UDP and TCP both, and they use UDP to send queries, a lot of queries, right? And they use TCP to do the actual transfer, data transfer. So they use both, but compared to the transfer traffic, the data transfer by TCP, those query traffic, although the number of packets is large, but the amount of traffic is small compared to the TCP traffic in P2P applications. So for P2P, it accounts for 70% of the internet traffic. And even although it uses both UDP and TCP, but TCP still account most of those P2P traffic in terms of traffic volume. Okay, and what other application would use UDP? The other one will be voice over IP. They would use UDP because it's hot real time. So those if you use Skype, you will find that you can find that it uses UDP, not TCP. And if you use teleconferencing applications, it use UDP too. However, if you use streaming, audio streaming or video streaming, some of the applications use UDP, some use TCP, and some use both. For example, in media player and real player, you could use either TCP or UDP. Okay, that's in real player and media player. However, on YouTube, they use TCP, which is called pseudo streaming. We will see that in chapter 6. It's called pseudo streaming, and it uses TCP with on the browser. So on the browser, you would see the video playing on your browser, and on the browser, the protocol is HTTP, which is on top of TCP. So running YouTube with on your browser is definitely you're running HTTP over TCP. So that's and it's called pseudo streaming. Okay, so you have seen this scenario. However, you will see either the P2P traffic, within the P2P traffic, the UDP part is not big. Okay, and for the streaming traffic, for the voice over IP and teleconference traffic, the resolution of running a teleconferencing session, usually you would only require several tens of kb per second, or hundreds of kbit per second. And because for teleconference, the video quality does not need to be very good. So the bit rate is not high. And for the streaming, if you see media player and real player, they exercise an adaptive codec scheme so that the bit rate will be as large as several hundred kbit per second, or as small as less than 100 kbit per second. So it's the bandwidth is not several megabit per second. So so for those applications who use UDP, they are not really a big bandwidth consumer. But there's one potential application which might consume high bandwidth, which is called IPTV, especially if it's a high definition. So and that is still on the horizon. So consider this. You have seen DVD quality. The DVD bit rate is like 3 megabit per second, which is high. However, if you have if you run some media player or real player program to view the program, it's only several hundreds of kbit per second, say between 100K to 500K bit per second. It's not over 1 megabit per second. So the quality is less, but the bandwidth is significantly reduced compared to the DVD quality. But if you want to have DVD quality running on the internet, then it's possible that your bit rate will be as high as 1 megabit per second. And if that kind of application, I mean high quality IPTV is everywhere, then you will see a lot of streaming traffic. Right now, the streaming traffic is not compared to P2P traffic. Streaming traffic is really small. But if you have those applications, if those applications prevail, then you will see a lot of these. And some of them will use UDP. Some of them will use TCP, depending on where they are run and the player they run on. If it's on browser, then they would use TCP. So these are the possible evolution, and so we can conclude that right now on the internet, TCP traffic probably is about 20% or less, maybe between 10% and 20% UDP traffic. However, over 80% to 90% are TCP traffic. And we know that TCP traffic we call them polite traffic. By polite, I mean they do flow control and congestion control. They would regulate themselves to prevent pumping too much traffic on the network or pumping too much traffic to the receiver. So we say TCP traffic sources are polite. However, UDP traffic sources are not polite, impolite. They send at the rate they need, they want. They don't do flow control, congestion control. However, if the real-time streaming traffic running UDP start to increase and account, say, like 30% or 40% or even 50% of the entire internet traffic, then you got problems to maintain the healthy to maintain the health of the internet. Right now, the internet is still stable and could work without too many problems. It's because the traffic is still dominated by TCP, and TCP is a polite protocol. But if UDP traffic start to increase significantly, we would have a problem to maintain the stability of the internet. In that case, people are proposing that we should turn UDP traffic to so-called TCP friendly. The UDP traffic should be regulated. They should also be regulated and become TCP friendly. Okay. It says, what is TCP friendly? It says it would need to respond to congestion. If there's a congestion, then they need to slow down and use no more bandwidth than a TCP flow. Okay, especially when they both receive the same network conditions, say suffer the same packet loss rate and RTT, then TCP flow and UDP flow, they should consume the same amount of bandwidth. And the TCP flow should not take advantage of the polite TCP. It's an interesting scenario, like on the real transportation system. Most of the drivers on the roads are polite, so they would stop at the red sign and go at the green signs, and they would stop at the hopefully at the stop sign, and so most of them are polite. So it's and probably only 5% or 10% of the drivers are too aggressive. Okay, and because 90% of the drivers are polite, so it's not a problem. However, if you consider on the road, 30% of the drivers are aggressive and impolite, then the traffic condition will be worse, right? And it's the same scenario here on the internet. It's stable because most of the traffic sources are polite. And it doesn't mean all the traffic sources are polite. Still, a percentage of the traffic sources are not polite, are impolite. And it's like 10% now. And if it grow into 20, 30, 40%, you would have a problem. So one day that might happen. We don't know whether it would happen. It depends on which application run, which application become the killer application later on. And one potential application that would use a lot of UDP traffic are either IPTV or a lot of voice over IP and conference calls. And for IPTV, they might use TCP or UDP. They could use both because they are sub real time. But for voice over IP and teleconferencing, they are hard real time, and they definitely would run on UDP. So they are the potential source of problems. And if that day comes, then we need to impose a TCP-friendly mechanism on them, on UDP. And there's a protocol proposed for this. It's a DCCP, which is not popular now, but they have prepared this protocol there, but not exercised popularly. It's called Datagram Congestion Control Protocol. It is meant to control UDP traffic. But since we are not in the stage of having a lot of UDP traffic. So we are not in the stage of exercising this protocol. So that's why it's not popular now. But the technology is there, and if UDP accounts a lot, then this protocol can be imposed to control UDP traffic so that it can become TCP friendly. And I have mentioned, there's a sidebar here about streaming, whether to run TCP or UDP on top of UDP or TCP. And it argues why not just use TCP alone. The reason is because if you use TCP, it has a retransmission mechanism, which might not be that needed in a streaming application. And it also has a rate fluctuation due to flow control. So the streaming application do not like TCP much. And why not just use UDP alone? The reason is that the UDP traffic are sometimes blocked by networks firewall. So some of the firewall would block the UDP traffic. Okay. Another reason is because some streaming applications still, for example, on YouTube. Why does YouTube run on browser? Why does YouTube run on browser, running on HTTP, which run on top of TCP? Why? The first reason is, of course, they want to use the browser. So you can use browser to view YouTube. The second reason is because if you run on TCP, and since this is soft real time, so it could accommodate a jitter buffer that absorbs the jitter at the price of increased latency. So I can increase the latency by introducing the jitter buffer to absorb the jitter. And since I have increased the latency, it doesn't bother me much if there are retransmissions for lost packets. Okay, if my jitter buffer say I have prepared a jitter buffer of 2 seconds, and 2 seconds will be long enough for any retransmission on the internet. So since I have introduced the jitter buffer and increased the latency, why not just do reliability and retransmission together, with retransmission together? Why not? So that's the reason why pseudo streaming becomes popular. First of all, it's browser. You can use browser. Secondly, you improve the viewing experience by retransmitting the lost packets. Okay. Okay, and so then it really depends on it really depends on which side you want. So you can choose to run streaming over UDP or TCP, and both have some advantages and disadvantages. So I'm saying for TCP, like YouTube, you have run on TCP with a price of increased delay, which is fine for sub-real-time traffic. And it's not okay for voice over IP or conference calls. Okay, the third issue is on the playback construction and path quality report. Remember that we said that we want the traffic source, I mean the codec to be adaptive. So instead of having the network control the stream, we would have the stream controlled by themselves. So instead of doing too much flow control by the network, we expect the traffic source to behave themselves. So, so the codec, the philosophy here is not. I have a fixed rate codec, and in order to pump a video quality, a good video quality, I pump 500 kbps per second all the time. And it's the network who should decide how to handle my traffic. If they have congestion, they do flow control, congestion control on my traffic, fine. And this kind of philosophy is not good. It's not good. We don't want that happen because, as I mentioned, if you pump 500 kbps per second constantly, and the network has suffered congestion, and they decide to flow control, congestion control your traffic to a half rate, then 50% of your traffic will be lost. 50% of your audio video data will be lost. Then at the receiver side, they would only receive half of the video audio data. The quality, then the reconstructed quality will be bad. So the better philosophy is for the traffic source, the codec, to behave themselves, to be adaptive to the network condition. If the network is suffering congestion, then your codec rate, your bit rate should be reduced from, say, 500 kbps per second to 200 or even lower. So usually that could be done by the codec technologies, by the so-called adaptive layered coding. By layered coding, it means that the audio or video data could be encoded into layers, from the base layer to the first layer, second layer, and if the network condition is good enough with abundant bandwidth, then you would send the audio video with all the layers. You would pump all the layers from the base layer to all the others. However, if the network condition is not good, the available bandwidth is not good, then you would send just the lower layers of the data. And in the worst case, then you would send just the base layer. And sometimes the base layer could be just consuming a small amount of bandwidth, a small bit rate, say from you can. I run a Slingbox. I don't know how many of you run Slingbox. It's a box that you can place on at home, connecting to your cable TV. And on one side, on one interface, it connects to your cable TV. On the other interface, it connects to the internet. So by doing this, you can view your cable TV from anywhere in the world, just like sitting in front of your living room at home. And I'm doing that because if I go abroad, I still want to see the news program in Taiwan, and I can just connect back to this Sling box. And it has an adaptive codec, and it is so adaptive that I can, if the bandwidth is abundant, then the bit rate will grow to over like 1 megabit per second, something like 900, 800 kbit per second. So that's a very high bit rate, should be close to DVD quality. Probably not yet DVD quality, standard definition, but not high definition. And probably a little bit lower than the DVD quality. For the DVD quality, you need close to 3 megabit per second. And it could be as low as 100 kbit per second. With just 100 kbit per second, I still can see the TV image clear, though the resolution is not as high. But the audio is no problem, because I think they treat the audio traffic as high priority compared to video traffic, because it is okay, but the video quality is not that good, but the audio quality should be maintained. If the audio quality is degraded, then I would not be able to hear clearly what the speaker is saying. Okay, and usually the audio traffic accounts less bit rate, much less bit rate than video quality. So putting the video quality, putting the audio traffic in at high priority is not a problem, because their bit rate is low. Okay, so you can see that they can reduce the bit rate from 1 mega 900K to 100K. It's a one order magnitude difference, and it depends on the network condition. So you need that kind of mechanism. I mean, that kind of adaptive codec. But how do you turn the codec to be adaptive? The codec needs to know something about the network. So you need to report the network condition or the path condition to the codec, to the source, to the sender. And that needs to be provided by the transport layer. But can TCP or UDP provide that? No. They have no field in the header, no header field to provide the path quality. And we need that in the transport layer, which is RTP and RTCP, real-time transport protocol, and real-time transport control protocol. Okay, here's the header field of the RTP protocol. It right on top of UDP. Providing extra information that the real-time application need. It provided the payload type. It means that this is for the sender, for the codec at the sender to notify the receiver, the prayer at the receiver. So the codec at the sender, coder and decoder. So at the sender there's a coder, and at the receiver there's a decoder. Okay, and for the coder to tell something to the decoder, what is my payload type? Okay, and then there's a sequence number, so that they would be able to handle packet loss or reorder. If some packets are lost, fine. I can know. If with UDP, if some packets are lost, you might not know it. I mean, the UDP protocol would not know it. The UDP receiver would not know it, that the some packets are lost. But so with TCP you know it, because the TCP, in the TCP header we got sequence number, but in the UDP header we don't have sequence number. So now they put the sequence number back in the RTP header. This appear in TCP but not in UDP, so they need to put it back. And they also have a timestamp, and the timestamp information is for the codec. I mean, the coder would timestamp the data, audio video data, so that the decoder will know whether this audio video data is late or not. Okay, if it has a timestamp that is 2 seconds ago, and my player would tell me whether 2-second delay is too late. If it's too late, then I would drop it. Okay, the receiver side would drop it. So it is timestamped by the sender and checked by the receiver to see if the data is too late. Okay, and it also has the identifier, stream identifier. Remember, in the first issue, we talked about the multi-homing, multi-streaming issues. The multi-homing, multi-streaming issue. We need in a session, in a real-time session, you got multiple streams, sometimes multiple audio and multiple video streams. So you need the identifier to identify that they belong to the same session. And then the data. So you need this in the RTP header. And also you need path quality reporting in RTCP. RTP is a data plane protocol. It carries user data. But RTCP is a control plane protocol. It does path quality reporting between the sender and receiver. And what does it report? It reports, so if the sender and receiver, at the end-to-end sender and receiver, they would, the receiver would report to the sender about what? The latency that it calculates, and the delay, the jitter, and the loss rate. And because the RTP header, in the RTP header we have timestamp and sequence number, so I would know the delay. I mean, if the sender send a data packet, and then it has timestamp and sequence number, so at the receiver it would know how long it takes for the data traffic to, I mean the audio video traffic to come here. So it knows how long this particular segment take to arrive. And also, if there's a loss, it would tell from the sequence number. So the receiver will be able to tell the delay and jitter. By jitter, it would because it know the delay of subsequent packets. So it would know the jitter in this stream. And because it has sequence number, it would know how many packets have been lost. Okay. So once periodically, the receiver would prepare an RTCP message and send it back to the sender. So at the receiver, it would do the measurement of these delay, jitter, and loss, and then periodically send RTCP message to the sender reporting the path quality. And these are the path quality. And we have said that the sender once received the path quality report in RTCP message, it would then adjust the codec. Okay. Because if the delay, jitter, loss is higher, are higher, then it means the path become the path quality become worse. Then it would reduce the codec rate. So by this, we by RTP and RTCP, we could control the real-time source and receiver beyond UDP. With UDP, we couldn't do any of this. But with RTP, RTCP running on UDP, we could. We will be able to do that. And here's an example of voice over IP using RTP. And it has multiple streams. So suppose the end-to-end is here, voice over IP gateway, and and these are traditional telephone network. So here is the termination point for an RTP session. So the RTP session doesn't come. So the RTP session doesn't come from here to here. No, because these are traditional telephone networks. So the RTP session comes from here to here. The termination point is here. However, there are multiple calls, traditional calls, that are multiplexed together into one RTP session. So I have an RTP session, but with which multiplex several phone calls. So then I would need to use the session ID, the session ID here, synchronization source identifier or contribution source identifier. So I need to use the session ID to identify, to differentiate them, because here on the internet I have just seen one RTP session. Within the RTP session there are multiple streams, and I could only differentiate them by giving them an identifier, which is in the RTP header. So I can do that multiplexing using different SSRC ID within one RTP session. So that's the one example that you would do that. Another example is the one I just mentioned in a digital TV program. Usually there is more than one session and one stream in a session. Usually in one session there will be 4 streams. One video stream, 2 audio stream, and 1 text stream. And in the future digital TV, there could be more than 1 video stream. See, if you want to have multiple display, I mean, on one TV screen, you would have 2 programs shown at the same time. One with larger screen, one with larger window, and the other will be smaller. Then you would have two video streams, and each of the video stream would have 2 audio streams and 1 text stream. So that would complicate the session. It's all together in one session, but many streams. And again, then you need RTP session ID in the RTP header to differentiate them and also to synchronize them. And here is another example. Another example that in a voice over IP gateway, in the codec, it has a codec that converts a traditional phone signal into digitized bit stream, and then further compressed to lower bit rate, and then send out. So basically, in the codec, it does the digitization and then compression. And here, what kind of codec scheme you use, what kind of format you use, need to be told, need to be specified in the RTP header. So that's why in the RTP header you see a payload type. Okay, so that pretty much cover the transport layer issue for real-time application, and we have explained why we need RTP and RTCP, and the difference between UDP and TCP for real-time applications. And one final question will be, where should we implement RTP and RTCP? We know TCP and UDP are in what? Linux kernel, right? They are in the kernel. And so one good place to implement RTP and RTCP should be in the Linux kernel, provided by the operating system. But they didn't. They didn't do that. They put it into a library. Most of the implementation are in library, RTP library here. So so they are implemented as a set of library functions that will call UDP socket. So they are implemented as library user space library functions, and those library functions, they would call UDP socket. So they write on top of UDP. So if you are a voice over IP application programmer, or you are a audio video streaming programmer, then what you would do is that instead of calling the UDP socket directly, you call RTP library functions. You include the library function, and then you include the library because you include, it means that it needs to be compiled. Okay, and then you call those RTP functions. You don't call UDP socket directly. You don't. You call the RTP library functions. Okay, so that's the way they implement, and it works pretty well. So if you see, if you check out the source code of those real-time applications that we will cover in chapter 6, in the next chapter, you will see that they all call RTP library functions. Okay, because RTP, RTCP is not implemented in the kernel.